Europa is one of the most intriguing moons of the solar system. It is the sixth largest moon in the solar system and fourth largest of Jupiter's 95 moons. While Europa is mostly made of silicate rock, its surface is frozen, covered with an estimated layer of water ice, 15 to 25 kilometers thick, which also makes the moon one of the most reflective in the solar system. With a large subsurface ocean thought to be hidden under an outer shell of ice, Europa may also be one of the most promising places in our solar system to find present-day environments suitable for some form of life beyond Earth. The water ocean, which likely has a real ocean floor in contact with the silicate rock at the bottom, may also have the chemical elements that are key ingredients to life. Although Europa is the fourth largest of Jupiter's moons, it's the smallest of the Galilean moons, the largest being Ganymede. With an equatorial diameter of about 3,100 kilometers, Europa is slightly smaller than our moon, about 90% its size. After Io, Europa is the second closest moon to Jupiter. Europa orbits Jupiter at about 671,000 kilometers from the planet, which itself orbits the Sun at a distance of roughly 780 million kilometers. This is more than 5 times further from the Sun than Earth is. Being so far away from the Sun, and having an extremely thin oxygen atmosphere, with barely 100 billionth of Earth's atmospheric pressure, means temperatures and light on Europa are extremely low. Average surface temperatures range from minus 227 degrees Celsius at the poles to about minus 177 degrees Celsius at the equator. Even in the warmest conditions, temperatures only reach minus 143 degrees Celsius. These temperatures are so low that even gases such as carbon dioxide would freeze solid. A day on Europa, which is measured by the time it takes it to complete one spin on its axis, lasts 3.5 Earth days. Europa always keeps the same side facing Jupiter because it orbits on its own axis at the same rate that it orbits the planet. This is a phenomenon called tidal locking or synchronous rotation, and it's the same thing that we experience with our moon. The most striking aspects of Europa's surface are its mottled, colored terrains and the linear fractures that crisscross most of its globe. Despite its appearance, it is the smoothest of any solid object in the solar system. Its highest peaks, of which there are few, only reach a few hundred meters tall, and has a relatively small number of craters, none of which reach more than 20 kilometers in diameter. This is in dramatic contrast to its neighbors, the two outer satellites Ganymede and Callisto, which have numerous large craters on the order of 50 to 100 kilometers in diameter. The crisscross streaks and splotches that run across the terrain are probably mostly due to relatively shallow fractures and different compositions of the ground, not the enormous canyons present on some other worlds. This smoothness means that Europa has a surface that's geologically young and constantly being reshaped. Estimates of the surface age of Europa range from 20 to 200 million years old, with the more likely age being between 40 and 90 million years. This suggests a significant resurfacing of the planet in the later stages of its history. The question of why the ice is being resurfaced and smoothed out faster than on many other worlds has not been definitively answered yet, but it probably has something to do with what's below Europa's surface. This frigid moon has a probable sea of salty liquid water beneath its icy crust. The ocean is thin relative to the moon's overall size, but it is thought to be more than 60 to 150 kilometers deep, which means it contains more than twice as much water as all of Earth's oceans combined. The chemical composition of the liquid ocean is still debated, since no direct sampling exists yet, but it's thought to be enriched in a combination of ions. Observations of Europa's icy crust have also provided clues as to what the subsurface ocean is made of. The icy crust is made of water ice with some carbon dioxide ice, but salts such as magnesium sulfate, magnesium chloride, sodium carbonate, and sodium chloride, common salt, have also been detected. Assuming these salts in the ice crust formed by freezing of the underlying ocean, this would suggest that magnesium, sulfur, sodium, carbon, and chlorine are all present in Europa's ocean. However, it is unclear from the ice crust alone how much of these elements there might be, as they could be influenced by processes occurring in the icy crust. or if there are any other elements, ions, or molecules present in the ocean. The presence of these salts also indicates that the ocean is interacting with the rocky seafloor, like on Earth. This causes the rocks and minerals to break down, a process known as dissolution, liberating ions into the ocean where they can form new minerals and become incorporated into the ice. But how can liquid water exist so far from the sun, where temperatures are unimaginably cold? The answer lies in heating from within. The reason for the higher temperatures of the ocean is due to radiogenic heating from the rocky mantle and tidal heating from gravitational interactions with Jupiter and the neighboring moons. In other words, Europa is constantly being stretched and squeezed by Jupiter's enormous gravity and by the gravitational pull of its sibling moons Io and Ganymede. This process generates heat inside Europa, preventing its ocean from freezing solid, and probably causes the long cracks that run across its surface. The exact size and composition of Europa's metallic core is unknown, but measurements of Europa's gravity and composition from future missions should help home in on its diameter. Europa's rocky interior lies between the ocean layer and the moon's core. Its exact diameter is also not precisely known. As Europa flexes due to the gravity of Jupiter, ocean water might seep into the uppermost portion of the rocky layer to be heated and interact chemically with the rock, loading the water with minerals and organic carbon-containing compounds as it flows back into the bottom of the ocean through cracks, fissures, or hydrothermal vents. Such a process could supply the ocean with building blocks for life, and with materials that could serve as food for simple organisms. The evidence that there is some sort of water or slush beneath Europa's surface is fairly strong, based on models of how a buried ocean would affect the ice above it. Measurements of the moon's magnetic field has also hinted that there is some sort of electrically conductive fluid, such as salty water, flowing under the surface. There are even images from the Hubble Space Telescope that appear to show huge plumes of water vapor erupting from Europa's south pole, although they are not high-resolution enough to be definitive. If the liquid ocean really is there, it could make Europa an especially promising place to look for life, because liquid water is crucial for life as we know it. Europa may have all the ingredients needed for life. Its ocean contains water, likely salts and minerals, energy from tidal flexing, and possibly underwater hydrothermal vents. On Earth, such vents host thriving ecosystems of bacteria, tube worms, crabs, and other organisms. Plus, Europa is as old as Earth, meaning it's had billions of years for life to potentially develop. If life exists there, it may be microscopic and adapted to life in a deep, dark ocean, just like some of Earth's extremophiles, organisms that live in extreme conditions, such as high temperatures or high pH. A 2026 study suggests that Europa's seafloor may actually be calm and quiet. On Earth, this would mean there wouldn't be enough geological activity to provide the conditions needed for life as we know it to develop. But this isn't to say that different kinds of life couldn't exist on Europa. After all, it's an alien world.